So, parallel circuit, commonly known as current divider. Okay, so when we connect two resistors across each other or more, we create a parallel circuit. It's said to be connected in parallel. What we get then is, here's our voltage arrow for the source. We've got a current flowing, total current flowing from that source. But at this point here, also known as a node, a connection point, we split into I1 going through the resistor R1 and I2 going through the resistor R2. We could label a volt drop there and another one there, but they are essentially the same voltage across both resistors in the pair. So where we had one current in a series circuit, we've and I do stress the fact all series, we have one voltage in an all parallel circuit. Yep. We'll also find in a combination circuit we've got one voltage across all resistors in a parallel section of that. That's where you, okay. But we've got two currents, I1 and I2. So the current splits here, but comes back together this side to become IT again. So we can use two resistors in parallel to be a current divider. Yeah? Yeah, there can be more circuits in combination as well, yeah, yeah. I mean, if you think about it, when you plug things in sockets, all the things, your 10 laptops in here, they're all connected in parallel. And the reason they are is because they all need 230 volts. And if they're all connected in parallel, they'll all get 230. If you connect them in, you divide in the volts. So I'll start 240 volt, 20 lamps, 12 volts each. They're connected in, but you lose one lamp, not good, they're connected in series. Okay? So that's the current divider circuit. Problem. 3 resistors, 66 33 ohms and 56 ohms connected in parallel to a 24 volt supply. Calculate the total effective resistance of the network. So we've got to find RT. Yeah. The supply current, IT, and the current in each branch. So we've got to find I1, I2, and I3. We better label them up. So here's IT, there's I1, I2, and I3. Formula for our no, you can't use product sum for 3, you're going to use it for 2. Don't forget the all to the -1 at the end. 15.8. How do I know that that looks a sensible answer? It's the total is always lower than the lowest one in the combination. The lowest one is 33. We got 15.8, so that looks okay. Yeah. Because if you think about it, the overall resistance to that current flow is less because there's 3 directions for it to go in. So that makes sense. That's again the underlying electrical principle, that because the current's got 3 different routes to go, it's much easier than if it only had 2 or 1. Yep. So the total 15.8 ohms for total resistance. So can we now calculate total current? IT is equal to, yeah, it is, but we don't know what they are yet. Dan, do we? We haven't calculated them yet. From what we know E over RT. 24 over 15.8 equals. It's a matter of breaking the problem down step by step, finding the next available thing. Yes, there is an equation sheet. Yes. I'm not sure I'll put Ohm's law on it though. That's fair for electrical science. 1.52 amps. Yep. What about I1? Yep, because that's all parallel, so we can go with E here, yeah? Over R1, 24 over, what is R1? 66. Answer? .36 amps, 360 milliamps. E over R2, 24 over 633. And lastly, I3, .56. Yeah. Hang on. 0.42, but 0.43. We all do them then. And the check is all add up to approximately 1.5 amps. Yeah, Kirchhoff's current law, which we will formalize after. Okay, so in your notes, in that second hand I gave you, on both you want to do, but on page 11, there's tutorial questions again, and answers will be provided once I get the material on the website. Alright, so 10-minute go at those questions, or the series ones if that's what you need.